Hello guys, so today's lecture 9 is about rank of a matrix. Okay, so let's talk about this very important idea of a rank of a matrix. So it has a geometric meaning, but let's start with more down-to-earth matrix definition. So let A be a matrix of size n by m or a field F. So basically this A is something like this with coefficients a11, a(n)(1) up to a(n)(m), n by m matrix. So then one can consider a subspace W inside F power n spanned by m vectors vi, where this vi is basically the column vector. So it's a vector a1i, a2i up to ani inside Fn. So that's a column vector, one of the columns of the matrix. And then so W is just the span of these vectors, v1 up to vn. And then definition is rank of A is the dimension of this W. So this is a very familiar setting. So for instance, if you take a matrix like 1, 2, 1, 1, 3, 1, for instance, then the rank of this matrix equals to 2, because actually vectors 1, 2, 1, 1, 3, 1 span F2. I mean, these two, for instance, form a basis. So remember in homework there were questions like, here are 3 vectors, find the dimension of the space they generate inside your big space. So that's exactly what the rank of a matrix does for you. And our goal is to compute this invariant, compute this rank. So goal is to learn how to compute it. And to actually do that, so the story is not very hard. There are some elementary operations which we will discuss, and then you can easily do it algorithmically. But more importantly, this will be the first goal. So second goal will be understand geometric meaning of it. And so this is more interesting maybe. Okay, so let me start with explaining the geometric meaning at first, and then we will talk about how one can compute it in practice and why that algorithm works. So here is the theorem. So let's suppose suppose L is a map from some vector space V to W, and E1 up to M is a basis of V, and F1 up to Fn is a basis of W. And then let matrix of L is a matrix of L, of course, in this basis. So then rank of this matrix of this matrix MOL is just the dimension of the image of L. So remember when we talked about linear maps, we said the dimension of the image is sometimes called rank, and this notation is consistent. So this is called rank of a map, and then the same as rank of the matrix of this map. So proof is completely straightforward. I don't know why I called it a theorem, even it's totally obvious statement. And the reason is very simple. So just because columns of W are vectors L of F1, sorry, L of E1 up to L of EM in the basis F1 up to Fn. So, I mean, literally, remember when I have a matrix of a map, what we do, we take these images of these vectors L of up to EM, and these are columns of the matrix. So basically, this vectors Vi will be just these columns, L of E1 up to L of EM, and L of E1 to the L of EM span, sorry, so this collection span image of L in W. So this was a part of rank nullity theorems that if you take a basis of V and look at the images, they actually span W. So they not necessarily form a basis, but they span W. They span the image of the map. If you take image of basis of V, it spans the image of linear map. And so now we see that basically dimension of the image is dimension of the space spanned by these vectors, which is dimension of the space of columns of this matrix, and this is exactly the rank. So dimension of the image equals to the rank of this matrix A. So that's the proof. Very, very simple statement. So basically now you can think of this computing of a rank as a way to compute a dimension of a subspace, concrete subspace of Fn, or you can think of it as a computing a dimension of the image of a linear map. And of course, since there is rank nullity theorem, you can think of it as a way to compute the dimension of a kernel of a linear map. So we will talk about it a little bit later. Okay, how shall we go about computing rank of a matrix? So there is a notion of so-called elementary operations. And so these are some very concrete ways to take one matrix and construct another matrix out of it. So let me just explain what they are. So there are 3 of them. 4 columns and 3 of them for rows. So the first one, which is called, so C1 will be first elementary operation for columns, and R1 is the first operation for rows. So suppose we are given a matrix. A is a matrix. This A11 to the A and M. And so what is C1? So C1 is an operation where you exchange 2 columns. So you just take 2 columns, so take some I and J and exchange column I and J. So for instance, one can take a matrix like 1, 2, 3, 3, 1, 1, take I equal to 1, and J equal to 3, and then exchange it to get 3, 1 to 1, 1, 3, and what happens, these 2 columns got exchanged. Okay, so this is the first column operation, and of course, so I'm not going even to, so this is C1, and so row operations are absolutely the same, but for rows. So R1 is same for rows. I mean, for instance, you can take a matrix, say 1, 2, 3, 4, 5, 6, 7, 8, 9, and if you want to exchange, take I equal to 2, j equal to 3, then what you get is 1, 2, 3, 7, 8, 9, 4, 5, 6. Okay, so that's one thing one can do. So second elementary operation is so C2 and R2 are, so C2 take some lambda, which is an element of the field but not equal to 0, and some I from 1 to number of columns is equal to m, 1 to m, and multiply ith column by lambda. So for instance, you take the same matrix like 1, 3, 2, 1, 3, 1, lambda equal to 4, and I equal to 2. So you take the second column, multiply by 4, and you get 1, 3, 8, 4, 3, 1. Something like that. And similarly for row, you can take any row and multiply it. So this is the second operation. And the third one is slightly more complicated and most important one. So let me explain what is C3. So take I not equal to j from 1 to the number of columns to m, and lambda inside f. Now it can be even 0, and add to ith column j's column times lambda. So again, what you do, you take for instance the same matrix. Let's take this one, and then you take, for instance, I equal to 2, j equal to 3, lambda equal to -1, and then what you do, you take the third column, multiply by -1, and add to the second, and you get 1, 3, 5, 3, 3, 1. So you take basically this column and you add it there, multiplied by -1. So this is the corresponding operation. And similarly, let's see, for instance, 1, 0, 1, 1, 1, 0, 1, 1, 1. And then you take, I want to do the same for rows. So for instance, you want to take the third row and subtract it from the first times -1, and you get 0, 1, 0, 0, 1, 1, 1, 0, 1. Okay, so this is the idea of these elementary operations, and so I want to prove a theorem about that. So theorem. So there are two statements. So first is every matrix can be transformed to a matrix of the form one, 1, 1, 1, 0, 0. So here, so this is a block matrix, which just means that there are like a bunch of blocks which are easy to describe. Here we have everywhere 0, everywhere 0, everywhere 0, and here we have identity matrix, where, so this is of course the same sizes, right? So this is n, this is m, and to specify such a matrix, we need to say how many ones are there, and the number of ones is equal to r, where r is the rank of A. So this is the first statement. So you can do this tumba-yumba operations many times. Eventually you get just ones on the diagonal, everything else is 0, and the number of ones is the rank. So that's the first statement. And second statement, which is a part of the proof of this story is that transformations C1, C3, R1, R3, all of these guys do not change the rank of A. So these are two very important statements. And actually, what you can see from here, yeah, anyways, let's just leave it like that for a second. Okay, so so this is interesting, and let's just prove it. And also, I mean, so actually the first part, the fact that every matrix is equivalent to this form, is roughly speaking an algorithm just to do that, which you maybe already know because you use it solving linear systems or equations. But let me quickly explain that. Okay, so let me start with some example maybe. So let's suppose I have some matrix like 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, or something like that. And I want to move it to this form using elementary operations. So how do I do that? So for instance, so what I do, I first look at the first column, and if there is something which is not equal to 0, I choose one of the elements here. For instance, this one is not equal to 0, and then I rescale my first row to make it equal to 1. I don't need to do it here, it's fine. So then I start subtracting it from every other column to kill elements in the first column downwards. And so here the first is not changed, the second is not changed, and the last one you just subtract and you get 0, 0, 0, minus 1. Okay, so now I look at the second column and I try to do the same thing. So what I do, I find here some non-zero element, exchanging rows and columns, move it here, it's already here, and then I start subtracting it from everything below. What I get is I don't do anything here. Similarly, I don't do anything here. And in the last case, I don't need to subtract anything, but I need to make it equal to 1, so I multiply the last one minus 1. So now my matrix is in what's called a triangular form. And so what I then start to do, I do the same with columns. So now I have 1 here, I can subtract it from every row to the right until I get all zeros. And so this moves to 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0. Then I do a similar thing with the second column, and this moves to 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, and I move all 0 columns to the right. So eventually I get 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and so I moved it to this form, and in particular rank of A equals to 3, because there are 3 ones here. So I have not done it very consistently. Please check it out. It's everywhere online in the textbook. So you need to know this algorithm, but it is very straightforward. It's very easy and easy to do in practice. Perfect. So this is how we compute rank. But now I will give a formal proof of the theorem because it's a little bit maybe helpful. Okay, so let's start the proof. So proof. Wait a second. Nope. Yeah. Okay, proof. So so let's start with part 2. So why row and column operations don't change the rank? So the proof is different for columns and rows. So first let's prove that. So claim is that column operations don't change the rank. So why is that true? So that's actually quite simple, and the reason, let's just remember what the rank is. So we had a matrix Aij, and one can think of this matrix as a collection of vectors. So basically kind of matrix consisting of vectors, v1 up to n by m, where v1 up to vm are inside Fn. And then the rank is, as we defined it, the dimension of the span v1 up to vm. So by the way, so this is just notation with left and right like angle brackets for the span of the subset generated by these vectors. Cool. So we have this rank. So why it does not change under elementary operations? So let's take, for instance, elementary operation column 1. So, and what it does to a matrix. So what it does, of course, you can just, so since we do something with columns, we do just something with vectors. And so what it does, it moves it to a matrix v1 prime up to vm prime, where v a prime equals vb prime for equals to va for equals to va for a not equal to I or j, vi prime equals to vj, vj prime equals to vi. So we just exchange two vectors. And since the set of vectors does not change, so this set of vectors does not change, then the span of vectors v1 up to vn is the same as the span of vectors v1 prime up to vn prime. So of course, rank does not change. So the idea is that actually for all column separations, what happens is that the subspace generated by vectors don't change at all. Like literally, this is the main idea. So with C2, it's also very simple. So we had a collection of vectors v1 up to vn. And then we have, so we move it to collection, so this was a matrix, and then we move it to a collection of vectors v1 prime up to vn prime, where va prime is equal to, so it equals to va for a not equal to I, and to lambda va for a equal to I. So one of the vectors where lambda is not equal to 0. So one of the vectors is rescaled and the rest are the same. But of course, so then we know that lambda va is inside the span of the vectors v1 up to vn, just because it's one of the vectors rescaled. And so it means that the span of v1 prime, vn prime is inside the span of v1, vn. But similarly, of course, one can do it vice versa, because lambda, remember, is not 0, so you can divide on it, and then you see that similarly span of v1, vn is contained inside span of v1 prime, vn prime, so it means that they are just equal. And then C2 does not change the rank. Change rank. Perfect. So simply again, the space does not change because when you scale one of the vectors, you get the same subspace inside Fn. So finally C3, again, it's the same idea, just slightly more involved. So we had this collection of vectors v1 up to vn, and we move it to v1 prime up to vn prime, where va prime equals 2. So it equals to va for a not equal to I, and it equals to va plus lambda vj for a equal to I. So we take one of the vectors and add it to another times lambda. And so again, so if one takes, so vector vi plus lambda vj, the linear combinations of vectors vi and vj, so it is inside of the span v1 up to vn. So the whole vectors v1 prime up to vn prime are inside the span. I'm sorry, I'm using here a very simple observation that if every vector in the set is inside the span, then their span is inside the span, because again we are looking at all linear combinations of these guys, and this is just the same as all linear combinations of these guys. And also what we know that, for instance, so if you take collection of vectors v1 prime up to vn prime, it has all vectors. So for a not equal to I, v a is inside the span of v1 prime vn prime, simply because just this va actually equals to va prime, so it's just written somewhere here. And for a equal to I, we know that vi prime is equal to vi plus lambda vj. So for a equal to I, we know that vi is equal to, so this is vi plus lambda vj, which is vi prime, minus lambda vj, which is just minus lambda vj prime. And so it means that vi is also inside the span of v1 prime up to vn prime. And then, of course, the span of all these vectors is, so v1 up to vn is inside vi1 prime up to vn prime. And then we conclude that v1 up to vn is just the same as v1 prime vn prime. So again, this transformation does not change the subspace, and so C3 does not change the rank. So this is the first claim. Column operations don't change the rank, and the reason is very, very silly. Just they don't change the subspace, so they don't change the dimension of the subspace. That's it. So that's very simple. So this is with column operations. With row operations, the situation is a little bit more tricky and a little bit more abstract. So it's more important to understand. Let me do that. Okay, next part. So now we want to show that claim is that row operations do not change the rank. And this is more interesting because you can easily see that if you have this matrix and you do this row operations, so actually what happens is something weird happens. So these vectors are, so the subspace definitely does change. So let's see abstractly what's going on. So let's suppose we have this vector space. So this is n by m matrix, and let's suppose we have this vector space Fn, and then we have inside W, which is the span of v1 up to vn. Perfect. And let's suppose that we do some row operations. So let's suppose that we did some of the operations R1, R2, R3, and we went from a collection of vectors v1 up to vn to a collection of vectors v1 prime up to vn prime. Okay, so then the question is why? Yeah, so what do they? What the separation actually is? And the statement is that actually, there exists an isomorphism say phi from Fn to n such that phi of v1 prime, vi prime equals to vi. Phi of vi equals to vi prime. So basically, I will show in a second that there is an isomorphism depending on R1, R2, R3, so which one we take and with which parameters, which moves these vectors to these vectors simultaneously. And of course, so then the space, the span of v1 up to vn using this isomorphism. So isomorphism is a map from our space Fn to itself, and so of course it takes a subspace generated by the span to a subspace generated by phi of 1, phi of vn. And so basically if this was say w and this was say w prime, then we have a picture where you have this vector space Fn inside two subspaces. And your isomorphism moves Fn to itself and moves w to w prime. And then, of course, this map from w to w prime, which phi does, it is also an isomorphism between these two spaces. I mean, because, you know, isomorphism has trivial kernel, that's one reason, and also there is an inverse one, which just, if you take the inverse of phi on the whole space, it will move this space there backwards. So, so then, if such thing exists, then dimension of w is equal to dimension of w prime, and thus rank does not change. So this is not a proof yet, because what I said here some claim that if we do one of the separations, there exists such an isomorphism. So this is a question, why this is the case. So if we show it, we are done. So let's consider some simple example before I just write down general statements. So suppose we have a matrix like 1, 0, 1, 1, 1, 1, 2, 1, 1, and suppose we do a column operation. For instance, let's do operation row operation R3, where I take the first, say, row and subtract it from the last one. And then my matrix moves to a matrix 1, 0, 1, 1, 1, 1, 1, 0, 0. And then my question is, okay, so I claim that there is an isomorphism which moves these three vectors to these three vectors. And of course, this isomorphism is really easy to write down. So if I had a vector x1, x2, x3, then I can just take this vector and move it to a vector x1, x2, x3 minus x1. This is literally what I do. I take the first coordinate and subtract it from the last one for each of the vectors. And so this is my phi. This is an isomorphism, and the fact that it is an isomorphism is actually very simple. And then we see that we are in the setting. So there exists an isomorphism moving these three vectors to these three vectors. So dimension of the space they span will be the same. So I want to show it in general, and this is very easy. So let's just do it. So for the first row operation, R1. So let's just take a map which takes vector x1 up to xn, to x1 prime up to xn prime, where xa prime equals to xa for a not equal to I or j, xi when a equal to j, xj when a equal to I. So this literally means that I exchange two of x coordinates. So this is phi, and phi is an isomorphism because just, you know, phi squared equals to identity. If you do it twice, you get your vector back, and so it means that there is an inverse which is just the same phi. And indeed, this is exactly what the first operation R1 looks like. So for R2, So you have some vector x1, xn, and you just multiply one of them on lambda. So where this xa prime equals to xa for a not equal to I, and lambda xi for a equal to I. So you just multiply one of the coordinates on I, and this is indeed, if you have a matrix, what will happen is the whole row will multiply by this lambda, and so this is an isomorphism, phi. And again, the simplest proof that it is an isomorphism is because you can do the inverse. So phi inverse is just similar map R2 with lambda prime equal to 1 over lambda. So if you do the same transformation backwards, instead of multiplying by lambda, just dividing by lambda, you are done. And finally, R3 is also very simple. So what we do, we take x1, xn, and we move it to x1 prime up to xn prime, where xa prime equals to xa for a not equal to I, and xi plus lambda xj for a equal to I. And again, if you want to do it backwards, you do the same map, but with minus lambda. And that's R3. And so there exists an isomorphism for each of these maps, which does this with these vectors. And so the rank is not changed under any of those transformations. So this finishes the proof of the claim. So this claim is proven. Again, the idea is that when you think of a matrix, actually this column and row operations are two very different things. So maybe this is something I will explain right now. That's a very important idea. Okay, so let me explain maybe in some other language what we were just doing. So imagine we have a map, a linear map, L, from V to W. Let's say Fm to Fn, as before, and then so it has some matrix, and there is a matrix A is a matrix of L, and we are trying to compute the rank. So this is what we were doing before, and then the idea is that so we know that rank of A is dimension of the image. So something very geometric. It does not depend on any choice of basis. So it does not change when we change a basis. Of Fm and Fn. But then just think about it. So if you have a basis of Fm, which is E1 up to Em, and then you have this basis of Fn, which is F1 up to Fn, and then we know that the matrix is just a matrix L of E1 up to L of Em. So this V1 is equal to L of E1 to the Vm is equal to L of Em, and then so basically the main moral of the story. So moral is that C1 up to C3, it is just change the basis of Fm, and R1 to R3 is change the basis of Fn. So why again? So because so R1 to R3 is change the basis of Fn, and this is indeed because when we change the basis here, that's exactly when we start to apply this isomorphisms from previous part of the story. And when we change the basis of Fm, so this is when we do something with E1 up to Em, and if we, for instance, take instead of like E1 E2, E3, for instance, we take something like E1 plus E3, E2, E3, that's exactly is the operation C3, and this is nothing but changing a basis in F3 here, where E1, E2, E3 lies. So from this basis to this basis. So basically, when you have a map, you can do an isomorphism here or there, and it does not change the rank, because this is something following from the fact that rank is dimension of the image. And this elementary operations, they do this change of basis in the source or in the target. So this is the main idea. But we have maybe proven carefully that they don't change the rank, and so part 2 of the theorem is proven. So now let's prove part 1. So part 1, and part 1 is really this algorithm to move any matrix to this form. So let me again explain it, but without too many details. So so proof by induction. And we will just reduce the question for nm to the question for n minus 1 m minus 1. The idea is that, okay, so you take a matrix, and you know this is A. So if A equals to 0, then we are done. It's already in the form where you have everywhere zeros. So if not, apply C1 and R1 to make A11 not equal to 0. So just there is some non-zero term. Let's just exchange the column where it stands and the row where it stands with the first row and column. And now we have this first term, which is A11, which is not 0. And everywhere we have something. So then we do, say, C2, for instance, where we take lambda equal to 1 over A11 and I equal to 1. So we just divide the first column by A11 and we get 1. Something, 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 something. So now the first element of our matrix equals to 1. And then one can do C3 and R3 to move our matrix to the form 1, 0, 0, 0, 0, 0, 0, 0, 0, something here. So this is because we can just take the first column and start subtracting it from all the rows, multiplying by the corresponding element here. So basically what we do, we take, for instance, so if this is ith row, then we will multiply our first row on minus a, this coefficient here, ai1, and then we will get 0 here and something else which we don't care about. And we do it for every column and every row, and eventually we get this form. And then just, of course, now if we do any elementary operations with a smaller matrix, so suppose this matrix will be called A prime. A prime is this kind of matrix. Then apply induction to A prime, and just do now these operations with A prime, and they definitely don't change the first coefficient, and the zeros will stay zeros, because when you do these operations, you don't affect the first row and column. And so you will move your matrix to 1, 1, 0, 0, 0, 0, 0, 0, and this will continue happening until you get actually just either you will go to 1, 1, 1, 1, and zeros beneath and above. Or what might happen is you go to, so you might do it until some time, but then you get zeros everywhere here, and there is nothing you can do. So this is the proof. And maybe this is a little bit technical to write down all details, so I hope this idea is clear, but you can read it in the book, or it's written in many places online. But probably from this proof you just need to remember mainly the algorithm. Okay, and eventually there was one last statement, so eventually we moved our matrix to this form where we have this identity matrix 1 1 1 1 0 0 0 0 0, and then there is a number r here. So r is the rank of A, because C1, C3, R1 to R3 don't change the rank. And so the rank of our matrix, so rank of A equals to this rank of this block matrix 1 1 1 1 0 0 0, but this is definitely R because we have a subspace and we have a bunch of vectors which are just 0, and these vectors which are linearly independent, so they just form a basis of the subspace and their number is R. So that's as simple as that. Perfect. So there is maybe one remark I want to make. So one can ask, what is the geometric meaning of this kind of matrix? So if you remember rank nullity theorem, so in rank nullity theorem we had a situation when we had a source V, target W, and we were trying to prove that dimension of the image plus dimension of the kernel is equal to dimension of V. And what we did, we basically chose a basis of the kernel here, which all goes to 0. And then we chose remaining vectors, and then they span the image. And their number was equal to the dimension of the image. So if you take this basis here, and any basis extending that, which is extending the basis of the image here, you will get that your matrix has exactly this form. So basically you can think of this form of a matrix, the fact that every matrix is equivalent to that, as a statement that for every map you can choose, you can change a basis in a way that you eventually get the basis which we constructed in the proof of rank nullity theorem. So that's maybe an idea behind this construction. So this is the end of this complicated theorem, the proof of this complicated theorem. And now let's prove some corollaries, all of which might be interesting.